So basically there's an aircraft, and there is a wing-mounted camera which is capturing the field of vision, towards the nose of the aircraft, and then from here, there is some cross-track error that is being estimated, and the idea is to keep the aircraft aligned to the center of the runway. And this is some video trying to show that it can stay along the center of the runway or it can veer off. But anyway, for our purposes, what we are getting is a feed of images, and then there is, I don't know why this net became so small. So there's supposed to be a neural network, and then it's not how it was showing. Maybe some resolution issue, and then it controls the way in which the aircraft is steered. So there is this TaxiNet controller which is sitting here, which is a deep neural network, and there is also a safe controller, or maybe just a human pilot over there, and there is a decision module which sort of switches whether this TaxiNet controller controls the aircraft or the safe controller controls the aircraft. And this decision module itself is a big decision tree, and for our purposes in this talk, we'll try to understand what is the decision module doing. Can we come up with an interpretable interpretation for it which is explainable? So so either it could connect it to this, or it could connect it to this, and this is based on work from Sajid's group. The question is that we are trying to understand what this decision module is doing. This is some huge decision tree inside, but we want to come up with a more easily understandable interpretation of it. And what we are told is that this decision module decides to trust the ML component or not based on some features, some predicates, things like weather condition, rain and clouds, time of day, the initial positioning of the nose of the aircraft with respect to the center line, the initial heading, and so on and so forth. And I think these are just two simulations showing that under different conditions it can behave differently. So in the top, under bright conditions, it's kind of following the center line. Veered off, okay, and here it is tracking the center line. So the point is, we want to understand what is this decision module doing, and for our purposes we'll try to restrict ourselves to decision diagrams. These are kind of generalization of BDDs one might think of. So we'll have some predicates which are clouds, rain, initial position, time of day. Ignore these numbers, we'll come to those later. And we have some explainability score, maybe based on the size of the decision diagram, which predicates are being used, and so on. And we want to see how accurately our interpretation is predicting what this decision module would have done. Really sorry, this. Is
it okay on your screen?
I think it's a resolution issue. No, it's not okay on my screen either. So you can see here it shows in very nicely, but the moment I put it in full screen mode. Okay, maybe I'll just show it here. So this is probably what a decision diagram could look like, that there are different categories of clouds, and if it's in some category, and if the time of the day is between 8 a.m. to 12 p.m. And if the position is whatever greater than equal to 2.5 meter from the center line, then there's an alert, otherwise there's no alert. So there is a huge decision tree implementing this, and we want to come up with interpretations like this, which are much smaller. And of course, they may not be able to mimic exactly what this is doing, but then we want to come up with some correctness metric for it. And we also want to come up with some explainability score. As I said, there's nothing very sacrosanct about what we are using here. I'll tell in more detail what we are using, but you'll see that it can be generalized to other kinds of scores as well. So maybe I should go back to I hope this doesn't happen in the other slides also. This one showed up fine, so I have no idea what's going on. So this is another interpretation for the same decision module, which has a lower correctness score but a higher explainability score. This is, I guess, you would agree that this is easier to understand what's going on here just based on the time of the day. But of course, this doesn't match up the accuracy of the previous one with respect to the black box. And here is something in between, which has an intermediate correctness score and an intermediate explainability score. So the point is, all of these diagrams are trying to explain that same decision module, and they're in some sense incomparable, right? As I'm trying to increase the accuracy of the correctness score, the explainability score goes down. As I'm trying to increase the explainability, the correctness score goes down. So there is really no way of saying that one is better than the other. Ideally, we should provide all of these options to the user, depending on whatever context. And then, so that's what we'll try to do. We'll try to synthesize these interpretations automatically for given correctness and explainability measures, and we'll try to explore the Pareto front for this. All right. So, let's try to define this Pareto-optimal synthesis problem. What we have is a class of interpretations. This is like our hypothesis class, right, which could be decision trees, decision rules. There's a syntactic class of interpretations which maps the input domain to the output domain. Each interpretation in that class maps the input domain to the output domain. There is a set of samples which we are obtaining from the black box by sampling the black box. So this is a subset of I cross O. There is an explainability measure, which I think the same problem is happening here. So there is an explainability measure which maps each interpretation here to a non-negative real number. And as I said, there's a large class of such measures we can reason with. I'll talk about the specific one that we used. Similarly, there's a correctness measure which says that if you give me one of these interpretations and if you give me a set of samples, then I can tell you, what is the accuracy of that interpretation with respect to that set of samples. And then what I would like to get as a result, as an output of this synthesis procedure, is an interpretation which sort of maximizes this tuple, which is the correctness score and the explainability score. But we realize that there could be things that are incomparable. So really, since I have a pair of numbers here, I'll get a partial order here. So I want to find out something that's maximal in this partial order, right? So that's the Pareto-optimal interpretation with respect to this partial order. So it's the, whatever maximizes this thing in that partial order, I would like to get the argmax of that. So this would give me a Pareto-optimal interpretation with respect to these two scores, and I would like to do this automatically. And more interestingly, if there are multiple such maximal things in the partial order, I would like to actually get all of those, right? At least one interpretation for each of these maximal tuples over here. Now, this is good, and we did try this out, and well, we came up with an implementation. We did some experiments, published a paper, and then we realized that this problem is at least it has scalability issues. So we are not able to scale it up very, very far. So we came up with an alternative definition of the problem, which is a slight variant of it, where we say, okay, instead of coming up with Pareto-optimal interpretations, we're going to come up with what we'll call locally Pareto-optimal interpretations, and we'll take some slack parameters for the correctness score and the explainability score. And what I want to find is an interpretation such that there is no other interpretation E prime whose tuple sits within a certain window around the tuple for the interpretation E I'm looking for, right? So here I'm saying that I should not have an interpretation E prime whose tuple is strictly greater than, the tuple for the interpretation I'm choosing, but it is not too much more. So this is the slack kind of talking about, right? And I'll show it pictorially what this means. And it turns out that finding such locally Pareto-optimal interpretations is slightly more scalable. We are able to do a little bit more. We are also able to come up with some kind of an anytime algorithm for it. And experiments seem to... So we can give this kind of guarantees, and experiments seem to show that, and once again I'll show you the results, that these locally Pareto-optimal interpretations are often very close to the actual Pareto-optimal interpretations. Okay, so this is basically what this means pictorially. So suppose I'm measuring the correctness over here, I'm measuring the explainability, whatever the metrics are. Let's not get into the specifics of the metrics over here. And let's say each of these points here corresponds to an interpretation. So there is a whole bunch of interpretations possible, each with varying scores for the explainability and correctness. And of course the Pareto surface is here. And what we mean by Pareto interpretations, Pareto-optimal interpretations, is that there is no other interpretation in this rectangle to the right and above it, right? Because I'm trying to maximize both the explainability score and the correctness score. So if the interpretation corresponding to this point is Pareto-optimal, it means it's not possible to improve both the correctness score and the explainability score at the same time. Yeah, Sebastian, you had a question?
In this plot, the Pareto curve is convex, right?
Yeah.
Is this something that that based on the metrics that you're looking at, that this curve is always convex,
No,
or else you're also interested in non-convex?
Yeah, it's not guaranteed to be convex. In fact, I'll show you examples where we get non-convex curves. Yeah, this is just to... this doesn't correspond to a real example. This is just for illustration purposes.
Okay.
Right. So these green circled points, these are the Pareto-optimal interpretations because there's nothing to the right and above them, right? All of these areas are empty. There are no interpretations over here. Locally Pareto-optimal interpretations. So let's say I define this slack, as I just mentioned in the previous slide, as a box like this, where this is delta C, which shows how much I can look locally on the correctness axis and how much I can look locally on the explainability axis. And so, of course, every Pareto-optimal point is certainly locally Pareto-optimal. There's nothing to its right and above. But there could be other points like these, which are within these purple diamonds, which are also locally Pareto-optimal, because if I put this box with this, these points at the lower left corner, then there's no other interpretation within those boxes. So they are also locally Pareto-optimal with respect to these two slack parameters. But of course, the other points over here are not locally Pareto-optimal, because whenever you place this box, you find something else within that box. So they're not locally Pareto-optimal. And our holy grail is to find these points. We will describe how to find these points, but it's computationally expensive, at least with the current state of the art. So we will say that, okay, we will also try to find these points and then incrementally try to move towards the Pareto-optimal points, depending on how much resources we have. Okay, so whether I'm talking about Pareto-optimal or locally Pareto-optimal, I need some guarantee that there are no other interpretations within a certain window around that point. And so how do we guarantee the absence of interpretations within a slack window? And here is where formal methods comes to our rescue. And so that's what I'm going to describe in the next few slides, how we can encode this problem as a constraint satisfaction problem and then try to appeal to existing constraint solvers. Okay, so the specific constraint satisfaction problem, it's actually an optimization problem that we're going to look at, is called weighted MaxSAT. So, probably most of you are already familiar with this, but just for the sake of completeness, what is this problem? Weighted MaxSAT. So we have a Boolean formula given as a conjunction of clauses, and we have a weight function which maps each of these clauses to some non-negative real number. And we want to find an assignment sigma that maximizes the sum of weights of all of the clauses that are satisfied by this assignment. Okay. So of course, if this formula is satisfiable, then there is an assignment that satisfies all of the clauses, and so then this maximum value would be just the sum of all of the weights of all of the CIs. But typically, the interesting case is when this formula is not satisfiable, and we want to find out what are the assignments that maximizes the sum of the weights of the satisfied clauses. So here's a simple example. So I have some 6 clauses over here. Let's say these are the weights associated with these clauses. Turns out that this formula is unsatisfiable. So if I take a particular assignment, let's say x3 is 0, x1 is 0, x2 is 1, then what I find is that this clause is not satisfied, right? Both x1 and x3 are 0. This clause is satisfied, this clause is satisfied, and so basically if I sum up the weights of the satisfied clauses, it's only the first clause that's not satisfied, rest of the clauses are satisfied, so it has a total weight of 10. Okay? And the weighted MaxSAT problem says find an assignment which maximizes this weight, the sum of weights of the satisfied clauses. So what we're going to do is that we're going to encode the Pareto-optimal interpretation synthesis problem in weighted MaxSAT, and we're going to do this by breaking up the problem into 4 parts. So the first part, which I'll call phi E, is a symbolic encoding of the interpretations in the syntactic class. So it's a symbolic encoding of decision trees, decision diagrams, whatever other thing we have. The second one is an encoding of the samples that we have drawn when we are trying to estimate the accuracy or correctness, and from which we want to synthesize the interpretation. The third is an encoding of the correctness measure, and the fourth is an encoding of the explainability measure. And we want to make sure that we come up with an assignment that maximizes both the correctness measure and the explainability measure, because that would kind of give us the Pareto-optimal solution. So we want to assign appropriate weights to the unit clauses. I'll just show you what it is. And this, we can then show that. So the point is that suppose I assign weights to the, suppose I assign weights such that if I maximize the sum of weights of some of the clauses, I get a high correctness score, and similarly assign weights to some other clauses such that if I maximize the sum of weights of those clauses, I get a good explainability score. And then if I take the sum of those two, the sum of the correctness and explainability score, as long as they are always non-negative, anything that maximizes the sum is guaranteed to be a Pareto-optimal point, right? Because if it was not Pareto-optimal, then I could increase it further, and so the sum would increase. So this immediately tells us that if I independently try to encode the correctness measure and independently try to encode the explainability measure, then I could just take their sum and say maximize this. That would definitely give me one Pareto point. It won't give me all the Pareto points, but then I'll have to go and search out the other Pareto points. So here is how the encoding looks like. I'll rush through this a little bit, because I think this is specific to decision diagrams that we encoded, can be changed if we have another syntactic class. So we are going to look at decision diagrams for the sake of simplicity with a fixed size k. Once again, for the sake of simplicity, the set of predicates which are going to annotate the nodes of the decision diagram. This comes from a fixed set of predicates with some fixed number of branches, and then there's some set of labels for the leaves. I mean, even for small values of this, the size just grows combinatorially. The space blows up very fast, the total number of decision diagrams. And so, oh man, this doesn't show at all. Okay. Yeah, I think I'll have to switch. Yeah, I have no idea what's happening. So, okay. So, so this is a formula which is basically saying that, you know, there are k nodes. So each node other than the leaves I want to be labeled with a predicate. And so this lambda IP is a Boolean variable which says if the ith node is labeled by predicate P, then this variable is true. And of course, if that is the case, then the ith node should not be labeled with any other predicate. We can't label the same node with multiple predicates. The second one is kind of saying that, well, if once a node has been labeled with a certain number of predicates, then it must have whatever number of childrens that predicate, right? So maybe there are clouds and there are 6 kinds of clouds, so there has to be 6 children for that. Or maybe time of day there are only 2 buckets, so there has to be 2 kind of buckets for this. So this is pretty much encoding that. That there must be 1 child of the ith node which goes to some other node, and this must happen for each of the number of children that predicate mandates. And this is just encoding saying that if the node I is labeled with predicate P, then it should be exactly, you know, there should be exactly BP children going out of it. You know, there should not be more than BP children going out of it, right? Because I'm going to have to keep these variables around because I don't know which node will get labeled with what predicate, how many children it will have. So I have to keep these extra variables, but then they must be set to false. So this is kind of encoding the syntactic structure. Any solution of this will give you a decision diagram labeled with predicates, which has the right set of children. Each node has the right count of children, and every decision diagram can be encoded as a satisfying assignment of this. Okay. What about the samples? So so we have a set S of samples, and for each of those samples, I'm going to label each of the nodes in the decision in this. So the decision tree is kind of, I've not fixed it up. It's a symbolic decision tree, kind of, right? And for each node in the interpretation and each sample, I'll have this variable MIS, and this is true if and only if the interpretation that satisfies, you know, the previous formula that I talked about. So if I take a satisfying assignment of this, that will induce values on this for a given sample. So this is true if and only if there is a path from this specific node to the leaf labeled whatever that sample's output label is, which corresponds to that interpretation. So once again, we don't need to get into the exact details, but this can be coded up as a, right? And this is just saying that finally, after doing all of this, if I say that the root node has index, if it has index 1, then M1s will be true if the root node is leading to a path which gives the right output for the sample S. All right. And finally, the 2 measures, the correctness and the explainability measures. So here is where we are using the trick from MaxSAT. We are saying, okay, I'm going to insist that all the samples must be labeled correctly. Right? So I'm going to add this conjunction over here for all the samples at the root node. So the root node must give me the right paths for all the samples. So of course, if my interpretation cannot do that, then some of these are going to be set to false. But then, you know, I'm going to count how many of those are true. That will be my the metric that I want to maximize. And similarly for the explainability measure, you know, we came up with an encoding of how many nodes are being actually used. Not all, we have a maximum of k nodes, but not all of them may be used. And what is the predicate that is labeling each node? And if a predicate is labeled by node P, then we want to assign it some preference weight for that predicate P. So, so once we have these, I mean, basically we have this bunch of unit clauses here. We are asserting all of them to be true, but of course all of them cannot be true. Right? So we're going to assign weights to them. So this is where I can say that maybe some samples are more important for me, right? So I have sampled the black box, but I'm really interested in some corner of the behavior space. So samples from there are more important for me. Samples from other corners are not so important for me. So I can weigh the different clauses here, the different unit clauses here differently. I can have different weights for different predicates. Maybe the time of the day is more important than the clouds, or maybe the clouds are more important than the time of the day, so I can weigh them here. But of course, all of these have to be user provided. These are parameters that the user can provide. And I could say that, how much would I like to provide as a reward for not using a node, right? And so once again, this. And then we put all of these weights, and then this just becomes weighted MaxSAT problem. And the weighted MaxSAT problem will try to find out the maximum sum of the weights of the satisfied clauses. So it will try to basically sum up the weights of all of the satisfied unit clauses over here. And as I just mentioned, that summing up explainability and correctness scores gives me a Pareto-optimal point when I maximize it. Okay, so that gives me one Pareto point. So now how do I find out the entire Pareto surface? So this is fairly straightforward. So once I've found one Pareto point, I can clearly divide the space into 4 quadrants. And because this is Pareto, therefore I know that there are no solutions here. And all the solutions here are not interesting anymore, because this is going to be better than all of them. So there are only these 2 regions that are remaining, and I need to go and recursively apply this technique over here, right? And so this sounds straightforward. The only problem that we encountered is that when we are trying to do the search over here, we have to constrain the correctness score to lie between certain bounds, the explainability score to lie between certain bounds, and similarly over here. And because this correctness score depended on the number of samples, so putting these extra constraints that the correctness score should lie between certain bounds, if this number of samples is large, this becomes a large additional formula that gets conjuncted every time. And but on the other hand, the explainability score, if we are looking for small explanations, that is not that much of a concern, right? Because it just depends on how many nodes are there, how many predicates are there, and so on. So we said, okay, if the number of samples is too high, it's the bounds on the correctness measure becomes the problematic case. So we're good. So we said that, okay, we'll throw out that part. So which basically means that once I've obtained a Pareto point, then instead of doing the search over here, I'm going to do the search in this entire space. Okay. And similarly, I'm going to do the search in this entire space instead of restricting it to, the correctness score bounds. So of course, what might happen as a result of this is that I might sometimes end up getting things like this, which are not really Pareto, right? But the interesting point is that the moment I get this, it's actually very easy to filter out, because it must already be dominated by an already existing Pareto point, whose correctness bound I did not put in the encoding just to keep the encoding manageable. So indeed, we get such points and then we throw them out. And every time we get such points, we are narrowing down the interval on the explainability axis. And finally, this just leads to only the Pareto points. So this is better than before. I mean, if we had the correctness score, it was really not scaling up. So we removed the correctness score, and then we saw that, I'll show you some statistics. We do get some spurious points here, but it's okay. Not too many. We can throw them out, and we can get the Pareto curve over here. But then what we realized is that even with this, the MaxSAT solving was turning out to be a bottleneck. And of course, to the formal methods community, this is not news. I mean, this is a hard problem. It's not very scalable, much less scalable than SAT. So then we embarked on this new approach, which is basically saying, can we find some good seeds in this space of correctness versus explainability scores? Can we find some good seeds here, and then can we do local search from there? So the overall idea is that we use some kind of learning or some kind of search techniques to come up with a bunch of local seeds. So here, maybe let's say some kind of search technique has given me these 4 seeds: P5, P7, P8, P9, and then I go and check in these little regions around this, which is given by the slacks for the correctness and explainability, whether there are any other solutions here. So here you will see that there is a solution within this window. So therefore, this is not locally Pareto-optimal, but these 3 are locally Pareto-optimal. So we remove that from here, and we can say, okay, therefore I have now obtained one subset of locally Pareto-optimal things. But now, if I have more resources available with me, every time I'm removing something which is not locally Pareto-optimal, it means I have actually found something better than that. And so I can now go ahead and repeat this search starting from there, right? So for example, here, just for the sake of illustration, I could repeat the search starting from here, finding this additional point, and then I repeat the search starting from there, finding this additional point. So this iteration goes on as much time and resource as one can afford, but at any point, whatever we are declaring as locally Pareto-optimal are locally Pareto-optimal, and the search doesn't consider things beyond that locally Pareto-optimal thing, right? Only things that are not locally Pareto-optimal. And so now it's easy to see that if you keep your delta C and delta E large enough, for example, if delta C is as large as the maximum correctness score, if delta E is as large as the maximum explainability score, and if you iterate around this sufficiently many times, you will either find a locally Pareto-optimal point, or you'll actually go and hit a Pareto-optimal point. Because if delta C and delta E are large enough, right, I will see other points dominating me, and from there I'll see other points dominating me, and then. Now, what should be the right value of delta C and delta E to induce us to actually reach the Pareto-optimal points? This is very specific to this landscape of where the interpretations lie, and this is something that we don't have a very guaranteed way of figuring out what the right delta C delta E should be, but for any given delta C delta E we can find out the locally Pareto-optimal points, and we also know that if we increase this, we are monotonically approaching the globally Pareto-optimal points. Great. So how do we find these good seeds? Just in one slide, basically we use multi-objective Monte Carlo tree search. So what is this tree search over? So what we do is we say that, okay, our decision tree is going to have at least one node, and then this node can be expanded in many different ways. This is saying that there are different kinds of predicates I could use to label over here. Each of those maybe has 2 children over here, and then each of those nodes I can expand further, or maybe I can expand further. So basically, this is how I'm exploring the space of the syntactic interpretation class. So this becomes an MDP where there are it's a 2-dimensional reward. Every time I go from one node to the other, I can talk about how has my explainability increased, how has my correctness increased, and so this is basically an MDP with a 2-dimensional reward, and then we use standard techniques from the literature for multi-objective Monte Carlo search to basically explore this space, timing out whenever our resources run out. So at that point we know that we have, we are basically relying on the properties of the MCTS to give us some good leads, and from there we do the local search. Okay, so I'm almost out of time. So the statistical guarantees are really PAC guarantees, so let me not spend too much time on it. So we have a set of samples. Obtaining an exhaustive set of samples is not practical, so how large should this set of samples be? So we appeal to PAC learning, and we basically find out the sample complexity for the given interpretation class, and we sample as many items from there. Okay, now how do the experimental results look like? So this was the auto taxi example, and this is the kind of curve that we obtained for the auto taxi example. This is convex. Yeah, Sebastian.
Sorry, I do have one question about the PAC guarantees. Is that a guarantee per point, or is it a guarantee on the whole curve?
Yeah, so we come up with a set of samples, and then with that set of samples we come up with the entire curve. Okay, so is this sample representative enough? Is roughly what this is saying, that if you sample at least the sample complexity number of times, then with high probability this sample is, at a qualitative level, with a high probability this sample is representative enough, and the entire Pareto curve is drawn with respect to that sample. So of course I could repeat the sampling, and then I would get another Pareto curve, and we did these experiments, and they kind of lie close enough. There are minor variations.
Okay, thanks.
Right. So this is how, for example, for the auto taxi example, we get a Pareto curve like this. This is the globally Pareto optimal and I have drawn here the decision diagrams that correspond to these different points over here, 3 sample points. So here, high accuracy, not so good explainability. Not so good explainability, I guess, is obvious from this diagram, but this has a high accuracy. This is somewhere in between. Accuracy is slightly lower, explainability is slightly higher. This has, very easily understandable, but the accuracy is much lower. And I think this kind of curve gives much more information than just picking one point and saying I've optimized some convex combination of the different scores, right? Because really, I mean, this and this are not saying the same thing, right? And none of this is strictly better than the other, because I mean, this is more explainable, this is less explainable, this is more accurate, this is less accurate, right? So it's, I mean, if I had points over here, then I could find something which strictly dominates them, but these do not have any other points any other interpretation which strictly dominate them. So this is about the auto taxi, which I have sort of zoomed down to a little bit. These are other things. So this is Sebastian, as I was telling you, that there are things which don't appear convex at all. This is from some other benchmark, bank loan and theorem prover. All of these finding the globally Pareto-optimal point. And from this table, you can see this is the sample complexity. This is the for a given delta and epsilon. So the number of samples is not too large. These are the Pareto-optimal points, and these are those extra spurious points that we computed but threw them out. And then there's a minimum time and maximum time, median time. And the unsat time, which is when we finally say that, because finally the search ends when we say there is no further interpretation in a certain window. So solving unsat instances can sometimes take large time, but in our experience this was quite okay. All right, so now what happens when we go to the locally Pareto-optimal thing? So this is the same autotaxi example, and here the notation is slightly different. So these circles here are the Pareto curve. The stars are what we got from the multi-objective MCTS. As you can see that it actually went and hit the Pareto thing, the Pareto-optimal things, except for this one thing over here. And then, of course, the unsat means that in these windows over here, so this corresponds to the delta C, delta A window. There are, of course, no solutions. We are, we have a guarantee about that. And this is saying that what is it that I obtained starting from the MCTS after improving it, if it was not locally Pareto-optimal. In this particular case, everything was already locally Pareto-optimal. But here is another case, another benchmark where the Pareto-optimal curve was here. MCTS gave us this point. For this one, it didn't give us the Pareto-optimal. For this point, it didn't give us the Pareto-optimal. It gave us these two things. And then over here, we were able to show that these are locally Pareto-optimal. From here, we actually found a better point, because this was not Pareto-optimal, not locally Pareto-optimal. So we found a better point, and then and this one we were able to show as locally Pareto-optimal. Similarly, from here, we were able to find a better point, and we were able to show that. So basically, when we are going from here to here, this window corresponds to this. This one actually got dominated by this itself, because when we construct the window over here, this dominated that. And so what you see is that what we finally ended up with is with this, and this, 4 of which are already Pareto-optimal. We missed this out, but we also got to know that there are no other points in this part. Okay, with the guarantees. Yeah.
Okay. It is zoomed in quite a bit, right? Can you on this benchmark, what happens for correctness more than 75%?
As you can see that this was the Pareto curve. So there is no, within the hypothesis class, within the class of interpretations, let's say I think this was whatever 10 nodes, decision trees with certain set of predicates, there is no interpretation over there which will give you 100% accuracy.
Okay, yeah, thanks, that clarifies.
Right, okay, and then these are for 2 other things. So once again, you can see that the MCTS does fairly good. It brings us quite close. In these 2 cases, the globally Pareto-optimal couldn't give us even a single solution. No, so this could not give us even a single solution in these two cases, but we already have things which are locally Pareto-optimal. If we could improve something over here, but then finally we timed out trying to show that those are locally Pareto-optimal. Similarly over here. There's another interesting experiment that we did is saying that, well, what happens if I reduce the amount of time taken or increase the amount of time available? And so this was done with 10 minutes MCTS plus 10 minutes local search, and this is significantly reduced, 2.5 minutes MCTS to 2.5 minutes local search on the same platform. And what you can see is that the global and when we are searching for the global Pareto-optimal, we give the full 20 minutes here, and here we give the full 5 minutes. So here the global Pareto-optimal curve was found here, and the local Pareto-optimal search gave us these regions and these points. When I reduced it down to 5 minutes for the global search, it could only give us this 1 point, whereas for the local search, we could still show that these two are locally Pareto-optimal. We found some improvements over here, and this one we were able to show that that's already. This we timed out over here. So basically, we were able to show these two as locally Pareto-optimal, and we were able to show, that there are some additional points here for which the Pareto-optimal test could not complete within time. So okay, to conclude, I described a way of doing Pareto-optimal and locally Pareto-optimal interpretation synthesis. Looks like local Pareto-optimal is a more pragmatic proposition than the globally Pareto-optimal. And Pareto-optimality is the best we can hope for in an absolute sense, but I think local Pareto-optimality is a good compromise in practice. Our experiments seem to show that multi-objective MCTS to give the good initial seed plus local search by constraint solving is promising. And in future, we are also, exploring other things like, so currently we looked at interpretation classes which are large but finite, very large but finite. So can we go to infinite cardinality with finite VC dimension? Can we use oracle guided approaches? Can we explore the relaxations in constraint solving so that we can maybe scale up even further? Okay, with that, I'll conclude, and I'll be happy to take any questions.
We can probably have time for 1 or 2 questions. I know we have already had a few questions, but we can certainly take 1 or 2 more. I have one. If no one's gonna, okay, I'll do one, and I think Sebastian has another one. I'm curious. This MaxSAT formulation that you gave. I'm curious how it relates or compares against just having a random constraint to then find a new solution in the Pareto front. Like if you think that would, like a random XOR constraint, if that would be enough exploration of the Pareto front with high enough probability, or do you think that would be completely infeasible? Particularly because they're two-dimensional, I guess is my intuition there.
No, that's a good question. So the point is, if you want to give an absolute guarantee that it's globally Pareto-optimal, then the random constraint may not work, right? I mean, by random constraint, I mean you're slicing up this space randomly, or
I was thinking more random XOR over the clauses, just so the MaxSAT will give you some other point on the Pareto front. It's still a MaxSAT, but you've just introduced a random constraint on the structure.
You want to add another formula in the MaxSAT formulation, so which would curtail down the solution space.
But in an unbiased way, so that you are unlikely to get the same solution you got last time, but or you can't get the same solution you got last time.
Right. So I think what happens when you start introducing random constraints like XOR constraints in the original formula, is that you have the total space of solutions, and then it will just restrict you to some subset of the solutions. Now, that subset of solutions could very well correspond to something over here.
Okay.
And then you're going to find the best thing over here, or it might even give you something over. I mean, you'll have no control over. I mean, so that works very well for model counting, because every subset of solutions is good enough for us. Here, I really want to look at subsets which are like maximizing something. So
just as a follow-up to that, I guess sounds like, Marcel, you're positioning that as a alternative to the MCTS plus the local search. So you generate a random solution and then you locally search around it. Is that because that I think would be a more
that would work. Yeah. I mean, if I come up with something, whatever, some random subset over here, I find a solution there. I mean, if that makes MaxSAT easier. And then from there, I start exploring local Pareto-optimal.
Yeah. Although that's but you're still saying do a MaxSAT, not that is you keep the optimize. Okay.
Yeah. So what random XOR constraints do to the solution space is that they really shatter the solution space, and so it is not immediately clear whether properties with respect to delta C and delta E would be preserved.
Okay, no, fair enough. Thank you. Okay, last question, and then we'll end the session.
So really nice talk. So the question is, the explainability is a little subtle, right? Accuracy is better defined. I would say that there might be multiple ways to quantify the explainability.
So I didn't get time to explain this fully. So we have just used this one way of doing explainability, but essentially, anything which can be encoded up as a polynomial sized formula over here. I mean, we don't want this formula to blow up too much, right? So, I mean, we have these symbolic variables describing what the interpretation is symbolically, and anything, for example, I could say that, okay, I want to take the squares of these things, squares of the weights of these things, and then sum them up. I mean, all of this can be encoded up in small circuits as small formulas.
So recently we developed a method we call fix. It's additive trees.
Mm-hmm.
So you basically feed recursively trees with some complexity constraint for the number of nodes.
Mm-hmm.
And for some medical problem works really well. It's actually different. So can you extend naturally to this complexity? We just count the number of nodes.
Number of nodes is already taken care of here.
No, but we have additive trees now.
Okay.
So we basically, our prediction is sum of trees.
Oh, yeah. So that I think should be...
But your way of complexity, because I cannot quite follow the exact... So is it the same as just counting the number of nodes, or it's not?
Yeah, so this one is counting the number of nodes, or rather this one is counting the number of unused nodes. So we want to maximize the number of unused nodes, which minimizes the number of nodes if I have a total budget on the nodes. And this one is trying to give preference to some predicates, but we need not have this if that's not important. And this one is of course the accuracy, so that presumably we want to keep. But I could have this for each of the trees that you mentioned in your set of trees that are additive, and I could add up all of those.
So it's okay, we can just
plug
it in,
we
just count the number of nodes for all the trees.
Yeah, the number of nodes for all the trees certainly can be encoded using this. I mean, I basically need to do this for each of the trees and then just have all of those as the MaxSAT.
All right, let's thank the speaker one more time.
Okay, thank you.
All right, and then I believe, let me check the schedule because I don't know if you have it off the top of your head. 3:15. Yeah, let's do that. 3:20. All right, so we'll meet back here at 3:20 for the last session.